Buying a robotics kit without knowing what you're looking for is like handing someone a CNC mill when they've never touched a hand drill. It's overwhelming, it's expensive, and chances are it'll end up in the back of a closet. I've watched families drop hundreds of dollars on advanced kits their kids weren't remotely ready for, and I've seen others stick with beginner platforms years after their child mastered everything they had to offer. My name is Kazuki Tanaka, and today I'm walking you through a systematic framework that matches your child's actual abilities to the right technical milestones, not just the age range printed on the box.
You're listening to the STEM Lab podcast. Quick heads up before we dive in, everything you're about to hear, all the research, the data, the script, that's 100% human verified and written by real people. The voice delivering it is AI generated, but the expertise behind it is absolutely real. If you've been listening for a while, thank you for being here. Seriously, it means a lot. And if you're just discovering the show, welcome. I'm really glad you found us. We drop new episodes every Monday, Wednesday, and Friday, and each one digs into the tools and strategies that actually help kids learn science, technology, engineering, and math. Today we're talking about how to choose a robotics kit that matches where your child actually is right now, not just what the box says. Let's get into it. This guide comes from years of running fabrication labs and watching kids progress from block-based programming all the way to Arduino C++. You'll learn how to assess your child's real skill level, decode the kit specifications that actually matter while ignoring the marketing fluff, and build a progressive learning path that prepares them for industry-standard tools. Plan to spend about 20 to 30 minutes working through this framework. It'll save you from costly mismatches and give you a clear roadmap from basic motor control to sensor integration and beyond. First, let's talk about what you'll need before you start. You need a clear picture of your child's current skill inventory. Can they follow multi-step instructions? Have they programmed anything before, even screen-free coding toys? Do they understand cause and effect logic? You also need to assess your technical environment. What devices do you have? An iPad, Windows PC, Chromebook, Mac? How reliable is your internet? Do you have available workspace with power access? Then there are learning style observations. Does your child prefer visual instructions or do they like to experiment? What's their tolerance for troubleshooting versus their need for immediate success? Budget framework matters too, and I don't just mean the purchase price. You've got to factor in expansion packs, replacement parts, subscription software costs. And finally, be honest about your time commitment, especially for the first 3 to 5 builds. Now, let's talk about step 1, which is assessing your child's actual programming foundation. Start here, not with age. I've met 7-year-olds ready for text-based coding and 12-year-olds who need visual block systems. If they've never coded, look for kits using physical programming. That means tangible blocks, directional tiles, or button sequences that create visible robot actions. Something like the Botley 2.0 works without screens and builds mental models of sequencing before you ever get into abstract syntax. These kits should deliver immediate, observable outcomes. Press 3 buttons, robot moves 3 spaces. No syntax errors, no debugging complex logic. Success rate above 80% on first attempts. If they've used visual programming like Scratch, Blockly, or they're transitioning from screen-free tools, you want icon-based or block-based robot control with conditional logic. Look for platforms supporting if-then statements, loops, and variables, not just sequential commands. The LEGO Education Spike Prime hits this sweet spot with a drag-and-drop interface that mirrors Scratch but controls actual motors and sensors. Your benchmark? Can they build a program with at least 2 nested loops and 1 conditional statement? If they're comfortable with Python basics or have tackled Arduino sketches, jump to kits running Arduino IDE, MicroPython, or C++. These platforms prepare kids for professional robotics tools. Check compatibility carefully because some Arduino-compatible kits use locked-down firmware that prevents real Arduino library access. The skill gap that catches most families is spatial reasoning and mechanical assembly. A child might code beautifully, but struggle if a kit requires complex gear ratios or structural problem solving. Watch them build something with Lego or K'NEX. If they follow pictorial instructions confidently, they're ready for 50-plus piece builds. If they need constant help, choose kits with color-coded parts and minimal mechanical complexity. Moving on to step 2, matching programming language to career pathway goals. This matters more than families realize. The programming language your child learns shapes which professional tools they'll access later. Block-based visual languages, the Scratch-style interfaces, teach computational thinking quickly. They're perfect for ages 6 to 10 or absolute beginners. But here's the limitation. You can't transition this skill directly to professional robotics environments. Industrial robots, research platforms, and engineering competitions use text-based code. I see block programming as foundational. It's essential, but not terminal. Budget 1 to 2 years here max before transitioning. Python has become the dominant language in educational robotics, AI development, and data science. Kits supporting MicroPython or CircuitPython let kids write actual Python syntax while controlling hardware. The LEGO Mindstorm's Robot Inventor runs Python alongside its visual system, creating a built-in transition path. Professional relevance? Python skills transfer directly to TensorFlow, OpenCV, and ROS, the robot operating system. Those are the tools used in real robotics labs. Arduino C++ remains the industry standard for embedded systems, hobby robotics, and maker projects. It's harder to learn initially. Syntax is less forgiving than Python, but kids gain direct hardware control and understand concepts like memory management. If your child shows interest in electronics, circuit design, or 3D printing custom parts for robots, Arduino-based kits open more doors. Professional path? Arduino skills lead naturally to microcontroller programming, PCB design, and firmware development. Don't fall for kits with proprietary programming languages. If it only runs on the manufacturer's custom software, your child learns a dead-end skill. Stick with platforms using Scratch, Blockly, Python, or Arduino. Those are languages with massive communities, free resources, and clear professional applications. Step 3 is decoding kit specifications that actually matter. Marketing specs mislead constantly. Here's what I check first when evaluating a kit in my lab.
Connectivity type determines future headaches. Bluetooth robots sound convenient until your troubleshooting connection drops mid-program. I've logged failure rates. Bluetooth kits average 1 to 2 connection issues per hour-long session, especially in homes with Wi-Fi congestion. Wired USB connections prove rock solid for learning. Robots needing constant cloud connectivity are deal breakers if your internet hiccups or you want to use them away from home. Sensor ecosystem defines learning ceiling. Count how many sensor types the platform supports, not how many come in the base kit. A kit with touch sensors and nothing else, your child will exhaust its capabilities in months. Look for platforms supporting ultrasonic distance, gyroscopes, accelerometers, color and light detection, and line-following sensors. Compatibility with third-party sensors, especially Grove or Quick connector systems, signals a kit designed for expansion. I've seen families spend $300 on closed ecosystems, then need to buy entirely new kits when their child wants to experiment with environmental sensing. Power system matters for daily use. Rechargeable battery packs win over disposables. You'll burn through AA's shockingly fast during intense build sessions. But check battery placement. If changing batteries requires disassembling half the robot, your child will run it drained and avoid rebuilds. Best systems use easily accessible battery compartments or standardized rechargeable packs. Software OS requirements? Verify before purchase. Some kits demand Windows-only apps. Others need iPads specifically, not Android tablets. Chromebook compatibility remains spotty. Many Arduino-based systems don't support Chrome OS natively. The Vex DOS system runs entirely in web browsers, eliminating OS headaches, but requiring consistent internet. Build durability for repeated experiments. This separates quality kits from toys. I drop test, stress connectors, and rebuild robots 10+ times to assess connector wear. Snap-together plastic connectors loosen after 20 to 30 rebuilds. Metal fasteners and gear-based connections hold up indefinitely. If your child's learning style involves lots of experimentation and teardown, invest in metal-heavy platforms like Vex or Tetrix. They're expensive initially, but last through multiple skill levels. Now we're at step 4, evaluating hidden costs beyond purchase price. That $150 starter kit? I've seen total costs hit $400 plus once families understand the full picture. Subscription software. Some platforms charge monthly fees for programming apps or advanced features. Lego's basic Mindstorms apps are free, but supplementary curriculum platforms often aren't. Scrutinize whether free versions have limited functionality. I refuse to recommend kits that paywall core programming features. You shouldn't need a subscription to access if-then statements.
Essential expansion costs. Calculate what's needed to reach the next skill level. Most starter kits include 1 to 2 motors and basic sensors. Adding a third motor, servo controller, or specialized sensor often runs $40 to $80. If the base kit can't accomplish interesting projects without immediate expansion purchases, factor that into your real cost. Replacement part availability and pricing. Kids break things, motors burn out, sensors get crushed. Check whether you can buy individual components or must purchase expensive sets. Arduino-based platforms win here. Generic components cost dollars, not dozens of dollars. Proprietary systems force you to buy from a single manufacturer at whatever price they set. Consumables and maintenance. Some kits use specialized batteries, custom cables, or wear items. Others run on commodity USB-C charging and standard cables. Over 2 to 3 years, proprietary requirements add up. Competition and curriculum costs. If your child gets serious about robotics, competition fees, field elements, and registration can exceed kit costs. Vex competition families easily spend $500 plus annually. That's not necessarily bad. Competitions drive incredible learning. But factor it into your long-term budget if your child shows competitive interest. Step 5 is mapping the kit to your child's 12-month learning goals. Forget vague learn robotics objectives. Define specific capability milestones your child should reach. Beginner targets. We're talking first robotics kit or first programmable kit after screen-free toys. Successfully build and program a robot to navigate a square path using loops. Add a sensor, touch or distance, and program a conditional response. Debug a simple program when behavior doesn't match expectations. Explain in their own words what a variable does. If the kit you're considering can't support these outcomes, it's either too simple, buy it only if your child is under 6, or poorly designed. Intermediate targets. Second or third kit, 6 to 18 months into robotics. Implement nested loops and multiple conditional statements in a single program. Integrate 3 different sensor types in one project. Design a custom challenge, not from instructions, and build a robot to solve it. Understand and troubleshoot mechanical failures like stripped gears or misaligned sensors. If text-based coding, write a program with functions or methods, not just linear code. Kits like the LEGO Education Spike Prime or MakeBlock MBot 2 hit this level well, with enough complexity for genuine engineering thinking, but not so much that kids drown in options. Advanced targets, 12+ months experience, ready for competition or specialized paths. Write programs using interrupts or asynchronous operations. Implement PID control for precise movement or balancing. Design and fabricate custom parts, 3D printing robot chassis or laser-cut mounts. Integrate computer vision or AI libraries like OpenCV or TensorFlow Lite. Contribute to open-source robotics projects or understand ROS basics. These goals demand Arduino-based platforms or more sophisticated systems. At this level, you're no longer buying kits. You're building capability to source components, design systems, and troubleshoot at a semi-professional level. The critical question is, does this kit create a natural bridge to the next skill level, or is it an isolated toy? The best platforms are part of ecosystems. Lego Robotics products connect to each other. Arduino skills transfer across thousands of projects. Proprietary one-off kits force you to start over when your child outgrows them. Step 6. Testing platform compatibility with your learning environment. The best kit means nothing if it doesn't work in your actual home setup. Workspace requirements: clear table space, consistent lighting, nearby power outlet. Sounds obvious, but I've seen families buy robots that need 4 by 4 foot floor space when they only have a small desk available. Some kits demand permanent setup. You can't easily store a half-built competition robot, and rebuilding from scratch every session kills momentum. Device and software reality. Install the programming software before buying the kit. Yes, really. Download the app, check system requirements, verify it actually launches on your device. I've troubleshot dozens of broken kits that were simply software compatibility mismatches. Windows 10 minimum, or specific iOS versions, or browser only with web USB support. These details matter immensely on day one. Internet dependency and offline capability. Cloud-based programming platforms fail during internet outages. If your connection is unreliable or you want robots for car trips or outdoor spaces, prioritize kits with offline programming capability. Some platforms let you code offline, then sync. Verify this works in practice. Support ecosystem matters more than you'd think. Active user communities, video tutorials, and responsive customer service determine whether you'll successfully troubleshoot problems. Before purchasing, search for the kit name plus troubleshooting or not working and read through the results. Strong platforms have detailed documentation and active forums. Weak ones leave you stranded when something doesn't work. Family support capacity. Be honest about your own technical comfort level and available time. Some kits assume parent or adult facilitator expertise. Others include guided lessons that kids can follow independently. In my fabrication labs, I've watched 8-year-olds work autonomously with well-designed beginner kits, and I've seen 13-year-olds need constant adult support with poorly documented advanced systems. Match the kit's required support level to your realistic availability, especially critical in the first 2 to 3 sessions when frustration runs highest. Step 7. Checking progressive path and future-proofing. This final evaluation prevents dead-end purchases. Expandability architecture. Can you add motors, sensors, and controllers incrementally, or do you hit a hard limit? The difference between 2-motor and 4-motor capability is enormous for advanced projects. Platforms with standardized ports, like Lego Technic connectors or Grove modular sensors, let kids experiment without compatibility headaches. Closed systems cap out quickly. Skill transfer to professional tools. Ask specifically, does this kit prepare my child for tools used in actual engineering? Arduino-based platforms clearly do. Arduino runs industrial automation, scientific instruments, and maker businesses worldwide. Lego Mindstorms connects less directly to professional tools, but teaches engineering problem-solving that transfers. Proprietary language kits that don't map to Scratch, Python, or C++ teach isolated skills with no clear next step. Community longevity and manufacturer support. This is harsh reality. Some robotics platforms get discontinued. Companies exit the education market. Before investing $200+, verify the manufacturer has been supporting the platform for at least 3 to 5 years and shows ongoing development. New sensors, updated software, active community. Established platforms like Vex, Lego Education, Arduino, and Raspberry Pi show commitment. Startups with single products, higher risk. Integration with broader STEM skills. The most valuable robotics kits connect to other disciplines. Robots that work with renewable energy experiments, integrate data logging for science projects, or support custom mechanical design deliver compound learning value. Isolated kits that only teach robot-specific skills miss opportunities. Competition and challenge pathways. Even if your child isn't competitive by nature, formal challenges provide structure and motivation. Check whether the kit is used in First LEGO League, VEX competitions, or RoboCup Junior events. Competition ready doesn't mean you must compete. It means the platform is sophisticated enough that others build entire competitive programs around it. Step 8. Making the decision matrix and executing the purchase. Pull all these factors into a simple comparison framework. I use this exact rubric in my fabrication labs when helping families choose.
Create a scoring table with these categories: skill level match, 0 to 10, perfect match equals 10, too easy or hard equals 0 to 4, programming language career relevance, 0 to 10, Python or Arduino equals 10, proprietary equals 0 to 3. Total cost of ownership, including expansions, 0 to 10, under $300 total equals 10, over $600 equals 0 to 4. Expandability and future compatibility, 0 to 10, open ecosystem equals 10, dead end equals 0. Technical compatibility with your home setup, 0 to 10, works flawlessly equals 10, questionable equals 0 to 5. Community support and documentation quality, 0 to 10, excellent resources equals 10, sparse equals 0 to 4. Score each kit you're considering. Anything under 35 out of 60 is probably a poor fit. Over 50 out of 60 signals a strong match. Trust your gut on enthusiasm fit. If your child is obsessed with Star Wars, a robotics kit using those themes might justify lower technical scores. Motivation trumps perfect specifications. If they're fascinated by AI concepts, prioritize kits with camera modules and vision programming support, even if mechanical complexity is lower. Start with the base kit, not the mega bundle. I see parents buy $500 comprehensive sets when a $150 starter would prove whether the child actually connects with robotics. Purchase the minimal viable kit that hits your skill level, use it for 2 to 3 months, then expand if engagement stays high. Exception: if you're absolutely certain, prior camps, consistent interest over 6+ months, buying the advanced kit up front can save money long term. Physical purchase logistics. Check return policies before buying. Some robotics kits have restocking fees or no returns on educational products clauses. If you're uncertain about compatibility, buy from retailers with flexible returns. For budget-conscious families, consider used robotics kits from school surplus sales or maker community exchanges. These kits are often built once and barely used. Now let's talk about pro tips and common mistakes. The age range trap. Manufacturers print conservative age ranges to avoid liability. I've watched 6-year-olds excel with ages 10+ kits and 12-year-olds feel bored by ages 8 to 14 products. Trust skill assessment over printed ages. Underestimating mechanical assembly difficulty. Programming often gets easier than building the physical robot. If your child struggles with fine motor skills or following complex visual instructions, choose kits with larger parts and simpler mechanisms. Lego-style snap construction beats tiny screws and precise bracket alignment. Constant forced updates that break compatibility or require newer OS versions. Before committing, check the manufacturer's update history. Constant forced updates that change interfaces mid-learning, frustration magnet. Buying for the child you wish you had, not the one you have. Parents with engineering backgrounds often choose advanced kits, hoping to share their passion, then wonder why their kid loses interest after one session. Match your child's actual demonstrated interest level. A child who tinkers constantly needs different tools than one who enjoys occasional structured projects. Skipping the learning curve preview. Watch YouTube videos of other kids using the kit. Read Amazon reviews specifically about setup difficulty and troubleshooting. Manufacturer marketing shows polished success. Real users reveal where things go wrong. If multiple reviewers mention took 3 hours to get software working or instructions are confusing, believe them. Neglecting the replacement part ecosystem. Fast-growing kids crash robots, strip gears, burn out motors. Before purchase, verify you can actually buy replacement parts without shipping from overseas or waiting weeks. Standard component kits, Arduino-based, Grove sensors, mean you can grab replacements from multiple suppliers. Proprietary parts create single-source dependency. Missing the transition moment. Kids show clear signs when they've outgrown a kit. They stop using it, complain about limitations, or ask, "Can this do more advanced thing?" That's your cue to move up, not 6 months later. I've seen families stick with beginner platforms for years past optimal timing, then wonder why their teen isn't interested in robotics anymore. Read the signals and act decisively. Let me tackle some frequently asked questions. What's the best robotics kit for a child with zero programming experience? Start with a physical programming system that uses tangible controls rather than screen-based coding. Something like the Botley 2.0 or similar screen-free robots let kids build sequencing skills through button presses and directional cards before introducing abstract syntax. These kits should deliver immediate visual feedback and success rates above 80% on first attempts. After 2 to 3 months of physical programming, transition to icon-based or block-based systems like Lego Spike Essential, which provides a gentler introduction to digital programming while building on established sequencing concepts.
How do I know when my child is ready to move from visual block coding to text-based programming with robots? Watch for these specific capability markers. They can consistently build programs with nested loops and multiple conditional statements. They understand and use variables purposefully, not just following instructions. They debug programs by reading through logic rather than random trial and error. And they ask questions about why the block does something or express frustration about block limitations. Typically, this readiness emerges after 40 to 60 hours of block-based programming experience spread over 6 to 12 months. The actual transition works best with dual-mode platforms like Lego Mindstorm's Robot Inventor that support both blocks and Python. Kids can write the same program in both languages and see equivalent results, building confidence before diving into pure text environments. Should I buy a kit compatible with Arduino even if my child isn't ready for that level of programming yet? Yes, if the kit also offers a beginner-appropriate programming interface and your budget allows the higher initial cost. Arduino compatibility future-proofs your investment significantly. Many modern robotics platforms run Arduino firmware on the back end, but present block-based or simplified programming interfaces for beginners. You're not forced to use Arduino IDE immediately, but the option unlocks as skills develop. This approach prevents the expensive restart that happens when kids outgrow closed platforms and need entirely new hardware to continue learning. The sweet spot? Platforms like the Arduino-based MBOT series or Elegoo robot kits that include both visual programming apps and full Arduino IDE support, letting you meet your child where they are today while keeping advanced doors open. How much should I expect to spend on a robotics kit that will last through multiple skill levels? Budget $200 to $350 for a quality expandable platform that grows with your child over 2 to 3 years, plus another $100 to $200 for incremental sensor additions, extra motors, and expansion components purchased as skills develop. Front-loading with a premium expandable kit, Lego Spike Prime, Vex IQ, or comprehensive Arduino platforms, costs more initially, but typically proves cheaper than buying separate beginner, intermediate, and advanced kits sequentially. The false economy? $50 to $80 basic kits that get outgrown in 3 to 6 months, requiring complete replacement rather than expansion. I've seen families spend $400 plus this way while thinking they were being budget conscious. For cost-conscious families, the better strategy is buying a quality used expandable kit from school surplus sales for $100 to $150, then investing savings into expansion sensors and components as needed.
Your roadmap is built. Now execute. You've got the framework. Skill assessment beats age ranges. Programming language choice shapes career pathways. Total cost includes subscriptions and expansions. Compatibility checking prevents day one disasters. Progressive learning paths protect your investment. The families I see succeed in maker education, they treat robotics kits as capability-building infrastructure, not entertainment purchases. They match tools to current demonstrated skills, watch for transition signals, and invest in expandable ecosystems rather than isolated toys. Take your scoring matrix, fill it out for 2 to 3 finalist kits, and make the decision. Then, this matters, schedule the first build session within 48 hours of the kit arriving. Momentum beats perfection. Your child doesn't need the theoretically optimal kit. They need a well-matched platform and your committed time in those crucial first sessions. I've guided hundreds of families through this process. The ones who spend 30 minutes on systematic evaluation up front, they're building competition robots 2 years later. The ones who impulse buy based on packaging, they're usually asking how to choose robotics kit for kids again 6 months later because the first purchase is gathering dust. Don't be the second group.
That wraps up this episode of the STEM Lab podcast. Thanks so much for listening. We release new episodes every Monday, Wednesday, and Friday, so there's always something coming up. If you found this useful, I'd be really grateful if you could leave us a 5-star rating and write a quick review. It genuinely makes a difference because it helps other parents and educators discover the show when they're searching for this kind of practical advice. And definitely subscribe or follow the podcast so you get a notification the second a new episode drops. Talk to you soon.